Okay, welcome back everyone. So in this last projectile problem example, we're going to be looking at the third type that you'll see, and this is probably the most complex. This is one where an object begins and ends at different heights. So for example, Jay Cutler throws a football with a speed of 22 meters per second at an angle of 40 degrees above the horizontal. The football was thrown from a height of 2 meters, and we want to find how long was it in the air, what was its maximum height, what was the horizontal distance it traveled, and what was the velocity 1.25 seconds into its flight. So really parts B, C, and D are similar to what we've done before, but part A is what's a little bit different. So first we're going to draw a picture. Okay, so here comes the greatest art in the world. So there he is. There's good old Jay. And he's happy because as of right now in 2012, the Bears are 4-1, but we'll see what happens. And so here's the football, and it's being thrown with a speed of 22 meters per second at an angle of 40 degrees. And the important thing is we're also given that it starts out at a height 2 meters above the ground. Okay, so what does the path of this projectile look like? Well, if we ignore the fact that it's spinning, so there's air resistance, blah blah blah, footballs will travel in a parabola. Okay? Alright. And so what we want to do is we want to find the total time of flight. And we need to make use of the fact that y initial is 2 meters up, but y final is 0 because it's on the ground. That means that delta y, which again is final minus initial, is actually -2 meters. So when we set this up for our delta y equation, okay, delta y is Vy initial times t plus 1/2 gt squared. And again, we need to write Vx initial is V initial cosine, and Vy initial is V initial sine. Okay, and I'm not going to write these out. By now, you should have some idea how to do that. So Vx initial turns out to be 16.9, and Vy initial is 14.1. And if you're unsure about where those came from, please look back at previous videos. Okay, so now what we have here is -2 for delta y. We have Vy initial is 14.1. Now, as long as you're careful and you have everything in meters, it's alright if you drop the units, because we're going to solve this equation for t. And like I said, as long as you're careful about things, it should be okay. So now we have a quadratic, and before we had the left side equal to 0, so we were able to cancel out a factor of t. But that's not the case here. So this is why we call these problems where delta y is not equal to 0. So if you've seen that before, so not equal to. That's what this little symbol means. Okay, so we basically have a quadratic, and just like in math, we want to make the lead term positive. It doesn't have to be equal to 1. As a matter of fact, it's a lot messier if you do that. So the important thing is to just write it so that you have everything on one side and the lead term is positive. Okay? So instead of solving ax squared plus bx plus c equals 0, we're going to have t squared, t, and a constant. So it works exactly the same way. Remember, quadratic equation, -b plus or minus the square root of b squared minus 4ac all over 2a. What? We have to use quadratic equation in physics? Gosh. So here we go. T is equal to positive 14.1, because b is -14.1, plus or minus square root of -14.1 squared minus 4 times 4.9 times -2 all over 2 times 4.9. Okay, if you do this correctly, you're going to get 14.1 plus or minus about 15.4 all over 9.8. So this means that we actually have two solutions. T is equal to 14.1 plus 15.4 over 9.8, which is about 3.01 seconds. And I can put the seconds back in because I was careful with my units to start with. Or you could say that T is equal to 14.1 minus 15.4 over 9.8, which is equal to negative 0.13. What? Hold on a second, that's kind of weird. Okay, so if we look at the diagram, 3.1 seconds is what we're talking about for the path right here. That's 3.01 seconds. Okay, but the negative is there, it's just not a true physical answer. The negative represents if the football had been launched from the ground and happened to have 22 meters per second at 40 degrees at 2 meters, well then this part of the journey would have been 0.13 seconds. And you can check that if you want, I'm not going to. But that negative 0.13 is accurate, it's valid, but our real answer is 3.01 seconds. Okay, so that's the thing about the uneven projectile problems that's most tricky. For things like finding the max height, this is pretty straightforward. There's two ways to do it. I'm not going to write all this out, but one way you could do it is you could find the time to go up from Vy final equals Vy initial plus GT, and then you could plug that time into the delta y equation. Or the other thing that you could do is you could just use the forgotten equation. So Vy final squared equals Vy initial squared plus 2g delta y. But either way, when you find delta y, we're only talking about the height something has gone up from the starting point. So this is delta y right here. In order to find the max height above the ground, we still have to add in another 2 meters. So we have to add plus 2 to find the max height. And I'm not doing the math for this, I'm just showing you how to do it. Okay. To find the horizontal range, or the distance traveled, we know this by now. Delta x is Vx initial times the total time of flight, and that was our 3.01. And this Vx initial was 16.9, and you can plug that in and see what you get. Okay? And then finally, if you want to find the velocity at 1.25 seconds, well, we know that Vx final is equal to Vx initial, like in previous ones, and then we can just plug in Vy final is Vy initial plus GT, and we can plug that into a final triangle and do Pythagorean theorem and find the angle like before. So nothing really too crazy about that. The important thing about these problems is understanding how to set up the quadratic equation from delta y.